Bridging the Pressure Gap in Transmission Electron Microscopy, Professor Patricia Kooyman from the University of Cape Town. We look forward to your talk. Thank you.
Yeah, thank you so much. Indeed, I'm at the University of Cape Town now, but before this, I worked at Delft University of Technology for quite a long time, and that's where I was involved in developing these nanoreactors with Henny Zandbergen, who was also involved in the first steps to develop the liquid nanoreactors that the last speaker will speak on. And what you see behind me in that small camera window is actually the view from my balcony at home at sunset. So Cape Town is really a marvelous place to be, with this gorgeous mountain like dominating the landscape here. And I'm grateful to Calliope for putting me in touch with the network so that I can present here. The thing is, even though I developed or co-developed these types of equipment, I don't at the moment have a system in South Africa. So I travel mainly to the Northern Hemisphere to use these systems. And one of the systems I use is the one at Oslo, where they also have a gas phase system, not only the biasing system. They've got some really nice equipment there at the TEM facility. I don't want everybody to go and run there because then there won't be any time for my experiments, but they're really welcoming to collaborations if you would like to, if you need these kind of experiments. So my question to Calliope already was a short introduction to what I'm going to speak about, because all of transmission electron microscopy will probably have prepared their samples just on the lab table. For powders, we usually a suspension in some fast evaporating liquid that doesn't change the samples, and then we put a few drops of that on a carbon-coated metal sample holder. But that's all just in air, and also many of the cutting techniques like the ultramicrotomy, they're performed in air. And if you do FIPSEM, then normally you transport your sample through air to the microscope afterwards. But especially in heterogeneous catalysis, which is my main application of transmission electron microscopy, many of the catalysts, while they are working, doing their catalytic processes, they are in a reduced metal state, which will oxidize straight away when it sees any oxygen. And some samples will even change when they're exposed to air. And ambient air, of course, is usually fairly humid. So what we had already developed at Delft a long time ago is what we call quasi-in situ transmission electron microscopy, which I will start with in a moment. And that prevents at least your samples to be oxidized in air, but you're still studying frozen samples. So you can only do before and after catalytic experiment characterization of your samples. So what we wanted to do was actually see the catalysts perform the catalytic reactions in real time. So that's what we call real in situ or operando. But first, let's briefly look at the quasi-in situ stuff, where you would use a TEM holder like this, and this black stripe here on the left is a Viton O-ring, and there's another one inside that lid that is sliding. So you can close off this holder airtight. So what you can do, you can prepare your TEM grid inside a protective atmosphere glove box, and they're usually filled with either dry nitrogen or dry argon. And then you can insert your sample into this special TEM sample holder, and then you can close it off inside the glove box, so the sample is completely surrounded by dry nitrogen or dry argon, and then you can transfer it to the microscope. And then you only open it once it's inside the vacuum of the microscope. So this completely prevents exposure to air of your sort of frozen catalyst or other material that's air sensitive. So I do have a system like this now here in Cape Town. So if anybody would be interested in collaborating and using that system, please do contact me, because then we can see if we can work out a way to collaborate on that. But that's not the main focus of this presentation, because people want to study the samples or the catalysts while they're doing their catalytic reaction. So also already quite a long time ago, Patricia J and Ed Boyce, actually while they were still at DuPont, they've moved to, I think, York University in the UK a while ago. They developed this kind of system where what you do is you take a sort of standard transmission electron microscope. For those of you who are used to doing microscopy, you might know the scheme where in the center where it says sample and stage, that's where actually your TEM grid is located. And then normally the sides of the microscope at that area are closed. They're just the straight walls of the microscope. But what they did is they literally drilled holes into the sides of the microscope so that they could let in gas, and then they would pump like an idiot, both at the other side where the gas comes in and at the same side where the gas comes in, to make sure that the total gas pressure stays below 50 millibars. Because the electron gun is a very high temperature electron emitter, and any even so-called inert gases that come in contact damage your gun, because they'll react to it, because because the electron gun is at such a high temperature emitting electrons. So next to this pumping through the pole piece, they also added additional pumping lines. And if you consider this kind of system, which Thermo Fisher now sells has already sold for a while as a commercial option, like I said, you can put about 50 millibars into the system before you start damaging your electron gun. But with most gases, you lose your resolution already at like 2 or 3 millibars. So you can study samples while they are reacting with gases, but you're limited to very low pressures. But this was a very important first step, and lots of interesting results have been and are still being obtained using these kind of microscopes. One of the disadvantages is that you really need a dedicated microscope that's adapted with all these additional pumping lines. Another disadvantage is that the complete sample holder cup needs to be heated, and it can react with the gases, as we will see in a moment. And then, as I said, Thermo Fisher sells commercial machines like this, and I've been lucky enough to play around with these types of machines, both at Helder Topsoe Company and at Arizona State University. And just briefly, if we go back to what kind of electron-solid interactions there are, we've got this very thin specimen here at the center, and then we've got the incident electrons that, of course, for a large part, just go straight through the specimen, which is the direct beam. So that's a beam that will give you a high contrast but low resolution image. Then only when you let the direct beam interfere with the elastically scattered electrons can you get high resolution, atomic resolution images. The thing is, any gases that are in the pathway of the electron beam, whether it's before or after the sample, they will give you a lot more scattering, both elastically and inelastically. So that creates a lot of noise in your image. And that's why when you go higher than a few millibars in the TEM setup that we just saw, you already lose resolution because there's just too many gas electrons that interact with the electron beam. And we've been trying to find solutions for that. So this is actually one of the first, when it was still called FEI, before it was bought by Thermo Fisher. This is one of the first commercial ETEMs available. And well, as you can see clearly from the picture, this is quite a while ago that I worked in Peter Crochet's group at Arizona State University and played around with this microscope for a week. On the left-hand side, you see the whole gas system with all the gauges and lines and heat tracing and valves. The pumps were a little bit further away, but they did often cause some vibrations. And then on the right-hand side at the top, you see all the additional electronic boxes that we need for this type of experiments, where you've got temperature control and pressure control and pressure measurement to use this type of system. So nowadays, of course, it's all integrated. So this is the current version of the Thermo Fisher TEMIS that you can buy as an ETEM. So that small white box on the left is all that you see now, and that's close to the microscope. And of course, all the controls are now integrated into the microscope user interface. But this doesn't show how much additional stuff you actually need, which of course the old machines showed very clearly. So one of the results that's been very famous is what Halder Topsoe produced on the growth of carbon nanofibers on a nickel particle, where you see that at the start of the process, the nickel particles are on a support material, but the strength of these growing carbon nanofibers is so strong that the nickel particle gets completely stretched out, and then the strain of that is so much that it dislodges from the support material, and it just gets by the growing carbon fiber. So if you look at that here, these are stills from that movie. We start at the top left, where you see that the elongating and that carbon layers are being formed. And then we go from left to right on the top row, and you see that the nickel particle is stretched and stretched much more and more. And then from left to right on the bottom row, you see where finally in frame H here, it dislodges from the support material. And again, it forms an almost spherical particle, which of course is much more favorable in terms of surface tension. And then the fiber keeps growing, and the nickel particle is pushed away from the surface. So as we've seen, we can only work at low pressure, but a few millibars is also still far from realistic operation conditions of catalysts. So with, as I said, Henny Zandbergen, who was then the microscopy professor at Delft University of Technology, and Frederick Kramer, who worked at the clean room facility. So he has a lot of knowledge about all the chip technology, what they call the micro electromechanical systems. We found a different approach to go to higher pressure and higher temperatures, which we called the nanoreactor. So it's a completely closed system where we've got electron transparent windows. Of course, I'll come back to that. We put the catalyst inside, and we can flow gases over the catalyst. We can measure the temperature in some way. And one of the important things is that the heater is on the vacuum side of the whole nanoreactor. So the heater is not directly in contact with your gases. It only provides the indirect heating of your bottom window. Because what I saw when I played around with Peter Crochet's microscope there at Arizona State University what we were studying was the carburization of iron oxide to iron carbide, which is a well-known Fischer-Tropsch catalyst to make synthetic fuels, to make biodiesel. But what we saw is that this platinum heater ring of the holder was completely covered in a very thick layer of soot after the experiment, which means that, like, even though we did see the carburization of the iron oxide, what was clear from this result is that like 99% of your carbon monoxide is actually reacting on your heater and not on your catalyst. So even if you see changes in your catalyst, that doesn't mean that that's actually caused by the gas composition that you put in, because before your gas reaches the catalyst, it has to go past this huge heater and can already react there. So that's one other big disadvantage. Again, it depends very much on what type of experiment you're doing, but for many catalytic experiments, the TEM is not the best way to go. So this is a little bit more realistic schematic of our nanoreactor, where you can see that we started out with having two separate bottom chip and a top chip, where you would put your sample on the bottom chip and then you would put the top chip on top. And then for our system, it was a bit difficult to align the top and the bottom chip. For the commercial systems, that's a lot easier because that's all geared towards user friendliness. But remember, we were inventing the wheel here. But we ended up with a chip that was thick enough to still handle it without breaking it just by waving it through air. You did have to be careful, of course, because those silicon chips are quite brittle, which also holds for the current commercial systems. And then you see there's a gas channel and there are electron transparent windows in the heated area. And of course, this must all still fit into a holder that will fit into the microscope. So this is the dedicated holder that we used, where you see a loaded reactor. You can see that the center is actually transparent to light. Those four silver colored strips that you see on the left-hand side are the four electrical who are used for measuring the resistivity of the, in this case, the platinum heater, but it's not necessarily limited to platinum. And the other two are used for adjusting the current that goes through the platinum heater so that you can actually adjust the temperature. And then the gas in and outlet are at the bottom of the holder viewed from this position, so you don't see that in this image. So this is a single chip where you can see the MEMS, the microelectromechanical systems membrane. So this is all made using chip technology. And here you see that those dark patches that you see are actually our electron transparent windows. And you see that there are lots of what we call pillars in between those windows. Those are on the one hand for strength, because if these very thin silicon nitride windows stick to each other, it's like cling wrap. Once it sticks to each other, it's very difficult to separate it again. So you really want to prevent them from hitting each other, because you can't really separate them without breaking them. And then these pillars are also, in this case, used to align the top and the bottom chip. So if the pillars on the top chip and the pillars on the bottom chip are exactly on top of each other, then the windows on the top chip and the windows on the bottom chip are also exactly on top of each other. So this is light microscopy of the assembled nanoreactor, where that white spiral is, as I said, in this case, the platinum heater. And in between the platinum heater lines, you see the pillars, the small circles. And in this case, we had oval electron transparent windows. So where you see those dark squares, that's where we actually have electron transparent areas. And then you see that outside of the heated area, the pillars are a bit wider just to give a bit more stability. So this is what it actually looks like in the microscope. So here you see at the bottom left and the top right, two of those small pillars. And then the top left and the bottom right, you see it's quite dark because that's the platinum heating spiral, and the platinum has a fairly high Z number. It's high in the table of elements, the periodic table. So it gives quite a lot of intrinsic contrast. And then you see that actually there in the center, at the top right of that square, those are catalyst particles that we can really study at atomic resolution because they are framed on both sides by these electron transparent windows. And this system will keep in the gases. So as a proof of principle, we studied the reduction of copper oxide on zinc oxide. The copper on zinc oxide, of course, is a well-known catalyst for those of you who know about catalysis. It's a well-known catalyst for both methanol synthesis and reverse Water-gas shift reaction. So what this ultramicroscopy paper describes is the whole reduction of the copper oxide particle on the zinc oxide. And what you can see here is that even at 1.2 bar hydrogen and 500 degrees centigrade, we still easily get atomic resolution even in the copper. So for this particular image, we saw that we had I think it was 1.8 angstrom resolution, but that's because that's the smallest copper D-spacing that we could measure. Of course, copper reduces much lower than 500 degrees centigrade, but we just wanted to show that it's very well possible, very easy to go to 500, 600, and as Calliope said, the commercial systems easily go to 1,000 degrees centigrade in 1 bar or a little bit higher of gases. Actually, Henny Zandbergen also made a system that could go up to 13 bar, but it's very difficult to find microscope owners that will allow you to use it in the microscope at that high pressure. So the commercial systems, most of them are limited to 1. So we've mentioned the commercial systems a couple of times. At the moment, there are 3 companies really that these type of systems, and none of them limit themselves to the gas phase systems, even though that's what I'm speaking on now. Actually, for catalysis applications, dense solutions and protochips are probably the best choices because they've got a low dead volume in their systems. And Hummingbird has a little bit bigger dead volume, so that's probably, in terms of the gas phase systems, more useful for example, hydrogen storage, where you mainly want to vary the pressure and the temperature and not so much the composition of the gases. Which brings me to some examples. And my first example is the copper oxidation. These data were collected by me and Stig Helve and Søren Vendelbo. Søren Vendelbo was the postdoc working on the project at that moment. But Søren Vendelbo was the one who actually did most of the data analysis and produced the nice movies that I'm going to show you. It's well known that copper oxide has a larger volume than copper metal, which means that when you start oxidizing copper particles, it doesn't stay a nice small sphere. And Kuykendall already observed this effect, I think in the 1940s. Where in the end you end up with hollow copper oxide spheres. That's why it's called the Kuykendall effect, because he was the first one to recognize it. And he already gave the theory, but couldn't be proven until we could do these kind of experiments. So if we look at this movie, and this is at 155 degrees centigrade, we start with a copper metal nanoparticle. But because it's already in a little bit of oxygen at room temperature inside the nanoreactor, it's already got an oxide shell. And now here, what you see is that suddenly the whole copper core oxidizes, and you can see that there's a couple of volcanoes where instead of molten magma, it's copper oxide that's being deposited. So what Søren spent a lot of time on is to do Bragg filtering and color coding. So it's the same movie that I'm going to show, but now it's color coded, where the red shows the metal copper and the blue shows copper oxide. Of course, it doesn't show everywhere because the orientation with respect to the electron beam has to be the correct orientation to actually show the despacings, the diffraction pattern in that particular grain. But the general gist will be okay, will be clear. So we see that we've already got a copper oxide shell at room temperature. And then when we heat up to, we see more and more activity. So we stopped heating at 155 because that's where it really sort of erupted. You slowly see the oxide shell growing, and then suddenly what's remaining of the core disappears because it all gets oxidized. The mechanism, as I said, it was already postulated by Kirkendall, is that the copper atoms diffuse along the grain boundaries in the copper oxide, and as soon as they then hit the outside atmosphere where there's oxygen available, they are oxidized to copper oxide, which is how you see this irregular shell growing, because the growing points are along the grain boundaries in the oxide shell. So that's one example. Another example is work on cobalt nanoparticles that PhD student Marien Bremmer did. This is one of the collaborations with Oslo, with Anja Sjastad there. Oh, I see that the original reference, that's not nice. I'm sorry about that. There's supposed to be a reference here to the paper of Irini Sakariki and Anja Sjastad that describes how these particles are being prepared. So they are prepared using oleic acid and a surfactant in heated dichlorobenzene. So it's heated to the reaction temperature. And then the cobalt precursor is injected. So this is called the hot injection method. And because the reaction mixture is already hot, the cobalt metal nanoparticles are formed practically instantaneously, which means that you form very and very small metal nanoparticles. And then we use these. Actually, what we wanted to do was to try and do the Fischer-Tropsch reaction, although we knew that that was maybe unfeasible at 1 bar pressure, but we wanted to try anyway. So we put them in one of the nanoreactors, and then we were flowing synthesis gas, so mixture of hydrogen and carbon monoxide. But as we expected a little bit, we didn't see anything happen even at 500 degrees centigrade. So then we said, well, let's see what happens when we just switch off the hydrogen. So then we were left with 1 bar total pressure, and the reaction mixture was 50% carbon monoxide in nitrogen, and we were at 500 degrees centigrade. And actually this Faraday discussion paper by Marien Bremmer was the main PhD student on this project. We'll also have the reference to that paper by Irini and Anja on how these particles are being made. So then what we saw happening was actually the growth of carbon layers. So here we've got a cobalt nanoparticle after 4 minutes after we switched off the hydrogen. Then like 5 minutes after we switched off the hydrogen, we saw something happening. And these carbon layers were growing and growing. And even after 40 minutes of reaction, for this particular particle, they were still growing. What we actually saw that as soon as a particle was completely encapsulated in carbon, it would stop growing new layers. So what we think is that the carbon monoxide needs somewhere some empty surface to anchor, and then it gets reacted to atomic carbon and carbon dioxide via the boudoir reaction. And then the atomic carbon diffuses through the cobalt nanoparticle to form layers at the other end. And the carbon dioxide, of course, is just removed with the gas phase. So we've got a movie of that as well. And this time is in minutes and seconds. So here already we've got at the top left, just as in the previous stills, because they were from this movie, we see that slowly more and more of these carbon layers are growing. And we have to fiddle a little bit with the focus, because with all these reactions, there's a little bit of change in height of the membrane that the particle rests on. So that's how we see these layers growing. And as I said, afterwards, we studied loads of different particles, and there we saw that as soon as a particle was completely covered in carbon, the growth of these monolayers stopped. So this is the insertion of monolayer, where it flips between two frames, and you can see that the whole packet of monolayers suddenly shifts away from the surface of the metal particle. So Marine has tried to quantify this. So these are the two frames that we were flipping between in the previous slide. And what he did was measure the intensity along this white arrow. And then where the black arrow is on the right-hand side is where the surface of the metal particle is, where the new layer is being inserted. So if you look at the bottom figure, you see that the cobalt particle itself is indicated in blue here, and then the carbon layers are indicated in gray. And you can clearly see a shift in the whole packet of carbon layers between the two frames. So that's where a new carbon layer has been inserted. We also saw twinning during this process, which we think is due to changes in the particle, carbon diffusing through it. So you clearly see that it goes from a single crystal nanoparticle to a twinned, and then double twinned, and then it seems to go back. So the particle changes the whole time. And this short stretch is looped here to show this clearly, where it goes from single crystal to twin to double twin back to single crystal. And here are some stills again from that last movie, where in the first frame there, it's a single crystal. Then in B, you see the single twin. And in C, if you look carefully, you even see three twins, one at the top left, one almost in the center, and then another one at the bottom right. And then in D, it's gone back to a single crystal again. And this is in a matter of like two seconds. So sorry, 2 minutes. So it changes really quickly. Which brings me to my last example, which is on the oxidation of carbon monoxide on platinum. This is, of course, a very important reaction because it's used a lot, amongst others, in car exhaust gas catalysis to remove carbon monoxide. It was known for platinum catalysts that oscillations were observed, but the main reason we chose this as one of the first test reactions was that there's a lot of literature available on it, also using scanning, tunneling microscopy, and other techniques. So what we did is we used, of course, diluted carbon monoxide in inert, and we used on purpose a huge surplus of oxygen to make sure that we could oxidize all the carbon monoxide if the catalyst was capable of doing that. And then the movie that I'll show you was recorded at 455 degrees centigrade, but there was a temperature range in which the phenomena that we will see would happen. So how we prepared the platinum nanoparticles is just to use the nanoreactor as a catalyst support material. So normally in practice, when you prepare a supported platinum catalyst, you will take some platinum salt that you make a solution of, and then you impregnate your support material with that. And then you decompose your salt by heating it in air. And then often you would heat until maybe 500 degrees centigrade. We only decompose the salt in air at 250. And then we reduced the platinum particles inside the nanoreactor, inside the microscope, but I'm not showing that. Then, of course, we made sure that all the hydrogen was pumped out and flushed with nitrogen a few times before we added this particular reaction mixture. And then we saw this happening. So there was a steady state, and then suddenly the heater power, which is the graph you see at the bottom, the heater power that we needed to input to keep the temperature stable at 455 degrees centigrade started oscillating. Now, for those of you who know the Helder-Topsoe premises, they're very close to a little train line. So we at first all thought, there were 4 of us working the microscope at that moment, all 4 of us thought, this must be the train. So we checked our watches, but it was not the scheduled, the train would pass every 20 minutes. It was not the scheduled train time. So we played around with it a bit, but we saw these oscillations multiple times. So then at first we thought, oh, well, the heater must be broken. So we took everything out of the microscope and prepared a different chip from scratch. And then we saw exactly the same thing. So then we were thinking, okay, well, then maybe it's real. So then what we did is we had a duplicate system at Delft University of Technology. So we brought these 2 nanoreactors that were already loaded and that gave this result at Topsoe. We brought those to Delft, and we again saw exactly the same thing. And then we loaded the 3rd nanoreactor that hadn't been tested at Topsoe and studied that at Delft, and again we saw exactly the same thing. So only then were we convinced that this was actually something real. So when you realize that this carbon monoxide oxidation is an exothermic reaction, this indicates that during those oscillations, suddenly we've got a much higher conversion of the carbon monoxide. Your reaction speed goes up. And as you see at the edge of this platinum particle, during the oscillations, there's a huge change, a huge movement of literally thousands of platinum atoms. So there's a lot going on here. And as you can also see that this change in morphology of that platinum nanoparticle is synchronous with the oscillations. So we did a couple of other things. We added here the Fourier transform. So there you can see the sort of virtual diffraction pattern of the image of the movie. And here at the top, we inversed the heater power we supply to use the heater actually as a micro calorimeter. So instead of showing the power we need to add to keep the temperature stable, what we're showing here is the power the catalytic reaction generates. And at Helder-Topsoe, there was a mass spectrometer available. So we also plotted the concentrations of, or the mass spec signals of carbon monoxide and carbon dioxide. Because we had such a big surplus of oxygen, that's completely out of scale, so we left that out, and it's only a small fraction of the oxygen that reacts anyway. So now if we look at what's happening, and this is slowed down a bit now, you can see that we've got a steady state, and then suddenly it starts oscillating. We see the particle oscillating, but we see that the Fourier transform stays almost stable most of the time. And then during these oscillations, we see that the total conversion of carbon monoxide drops to almost, or increases to almost 100%. So the carbon monoxide concentration drops to almost 0%. And then when the oscillation stops, and it stops spontaneously, we see that the carbon monoxide conversion goes back to the previous steady state conversion. So we're still not 100% sure what actually triggers this phenomenon, but it's definitely clear that during the oscillations, the catalytic activity is much higher. And we know that the more faceted morphology is stabilized by adsorbed carbon monoxide, and the more spherical morphology is stabilized by adsorbed oxygen. So somehow the system switches very quickly between completely carbon monoxide covered, completely oxygen covered, completely carbon monoxide covered, completely oxygen covered. We don't have all the answers yet. We're still working on this, although Søren Vendelbo has moved on and Stee is now professor at DTU, so he's not working at Haldor Topsoe anymore, but we're still trying to tie up all these loose ends. So we are working on another publication where we also include gas phase concentration measured by eels of the carbon monoxide and the carbon dioxide. And with these loose ends, I'd like to thank you for your attention and leave it at that for now.